Cool, isn't it? The Hall effect, which I don't really want to talk about today. I want to talk about that little guy, which is a Hall switch. But anyway, if you have a current flowing through a conductor, the black bar here, and at the same time there is a magnetic field going through it, then you can measure a voltage at its sides. The reason being, the electrons flowing through the conductor are deflected by the magnetic field to one side. For details, please refer to the Wikipedia article. I put a link down in the description. It even has an animation. To actuate my Hall effect switch, I got here a collection of 4 different magnets, ranging from a quite powerful neodymium one I probably got out of a hard disk teardown. Please refer to my teardown playlist card here, link in the description. 2 medium strong ones that might be neodymium or not. And finally a very weak run-of-the-mill fridge magnet. The Hall switch I'll be using is the Diodes AH3582, a high voltage, high sensitivity Hall effect omnipolar with internal pull-up resistor switch. That word is actually missing here from the headline. I choose it because it's very cheap, very easy to use, just VDD, ground and output, and it has a very wide supply voltage range. The typical application circuit is really minimal. Just give it a supply voltage of 3 to 28 volts, add a decoupling capacitor 10 nanofarad to 100 nanofarad, and you get an output. In the functional block diagram we see that the output is pulled down to ground via a MOSFET. There is a current limit, little shunt resistor here and circuitry, and it's pulled up by this resistor. The Zener diode just clamps the output voltage to the operating maximum of 28 volts. The output on voltage is between 0.2 and 0.4 volts, so the output is pulled low when a magnetic field is present. The internal pull-up resistance is between 10 and 18 kilo ohms, and the output current limit for that pull-down transistor is between 30 and 55 milliamps. Output high is of course the supply voltage, so we can connect that directly to a microcontroller or to any other logic if we choose VDD accordingly. Or we can drive a very powerful LED with it. A cursory glance at the timings shows us it's all in the microsecond range, so we should have no problems measuring magnetic signals up to a few hundred kilohertz. By the way, omnipolar means that it doesn't care about the direction of the magnetic field. It can either go north-south or south-north. There are also unipolar switches available, and there you have to take care about the direction of the magnetic field. Cool, isn't it? And I won't draw a schematic for that circuit. Power supply with a 9-volt battery, negative goes to the ground pin, positive goes to the VDD pin, and positive also goes through a 3.6K resistor and a diode, anode, cathode to the output. So the LED is switched on as soon as the transistor here pulls the output to ground. We already saw that thing in action with that neodymium magnet, and it seems to activate it at, 5 millimeters? Oh, something like that. That small one here, does it at full 10 millimeters. Wow. The medium-sized one, 14 millimeters. And finally, our weakest magnet from the fridge. Also. 10 millimeters. Easily. So I wonder if I'm using the big one not correctly, but no. It seems that the arrangement of the magnetic poles on that thing are not very suitable for this application. I rearranged the parts on the breadboard, it's still the same circuit, so I could fit the sensor along the axis of my Proxxon drill, 22,000 RPMs maximum. If you want to see a review of that thing, card here, link in the description. Anyway, let's zoom down. I snapped the smallest of the magnets that worked so well in our experiments to the axis here in my drill, and now if I turn it, the LED comes on once every rotation. That's not a given. Remember, this is an omnipolar switch. It doesn't care about the direction of the magnetic field lines going through it. So if I put it a little bit closer to the axis, the LED comes on because the magnetic field extends on both sides of the magnet. Yeah, north and south or south and north. I can't tell. The little thing can't tell either. So that is something you have to consider in such an application if you use one magnet and an omnipolar switch. Of course, you don't have that problem if you are using an unipolar switch, which is sensitive to the direction of the magnetic field lines. I found a second of these little magnets in my stash and I put it on the other side of the axis, so it is balanced. Remember, that drill can do 22,000 RPMs and it starts at 5,000 RPMs. And now we get reliably 2 pulses per rotation. We just have to keep it in mind for later. I will secure these now with some tapes. I don't rely on just the magnetic force for them not to fly off. And yeah, we let that thing turn. I buried the magnets under some reinforced tape here. We call this in Germany Panzer tape or tank tape because it's that strong. And yeah, before I switch on, and it's still working, 2 pulses per rotation, I will put on some additional safety glasses over my normal ones. Because, you know, shit happens. Fire in the hole. I don't know if you can see that, but yeah, it flickers. And that flicker should have been about 4000 Hertz. Guess it's time to break out the Arduino to make sense of the signal. Okay, I tried to arrange the windows on the screen so you can still see the scale here and the real-time signal as it's coming in from this side. Safety squints on. Fire in the hole. Wow. Well, that here says 5,000 RPMs, but we are almost at 8,000. Let's turn up the volume. $10,000, 12,000. 16. Oh, almost 24,000. Woo! Okay, let's have a look at the details there on the bench and then at the code. The circuit is still basically the same, I just moved it to another breadboard with a nano on it. I added the 100 nanofarad decoupling capacitor at the VDD pin to ground and my series resistor for the LED, we have now the Arduino 5V rail here, is down to 1.6K, but that's it. And the whole setup is a little bit sturdier now. But what I really wanted to show you is, while experimenting, somehow the magnets shifted. And so I get, and that's important, only one pulse per rotation. Okay, let's move on to the code. I'll be using in this code basically the same interrupt technique I already introduced in the rotary encoder video. Card there, link in the description. Anyway, I have a constant byte here, that's my AH3582 pin, and it's pin 2. Please note, for a nano with an ATmega 328, it has to be pin 2 or pin 3 if you want to use an interrupt with it. My measurement period is 100 milliseconds, so I count the pulses from the sensor for 100 milliseconds. And I have a volatile unsigned integer pulses, where the pulses are counted in an interrupt service routine. Therefore, it has to be declared as volatile. In my setup, I initialize my serial with 1 megabaud. I initialize my pin as input pin, and I attach my interrupt routine, which we will see later down, to the pin of my HA3582 on the falling edge. Doesn't really matter. In my loop, I have a buffer variable, pulses read, which I use to buffer the value of the variable pulses, which constantly changes due to the interrupt routine. I set pulses to 0 and start counting. Wait for 100 milliseconds, yeah, my measurement period. And then I buffer the value in the variable pulses into my pulses read. Finally, I print that out to the Arduino serial plotter. And I do some conversions here, of course. Pulses read times 60,000, 60,000 being the number of milliseconds in a minute. Yeah, we want to get rotations per minute in the end. And that is divided by the actual measurement period, so 100 milliseconds. And that's it. Then we have finally the interrupt routine, which does nothing but increment the value of the variable pulses each time we get a falling edge from our sensor. And I still have my safety squints on, don't I? You could have said something. That's it for today. You saw these thingies are really easy to use. The circuitry is primitive, the code as well. The most tricky part is probably, getting the magnetic stuff right when you are really measuring RPMs. But, just using them as a magnetic switch, and I haven't shown you code for that. You can do that by yourself. Basically nothing to it. I hope you enjoyed it. Bye.